think I'll introduce you and then you can get started. So
Wonderful.
Will is a co-founder and the CEO of Planet Labs, and his company works on using satellites to help humanity. He was a scientist at NASA and has his PhD and master's in physics, and is a postdoctoral fellow at Harvard and George Washington University. And I wanted Will to give this mentor talk because ever since I met him, he has been an inspiration to help the world, and I have seen him manage to pursue his dream while also living his life through service, and it's been super inspiring. So without further ado.
Well, look, firstly, a really pleasure to meet you all. Thanks very much, Jada, for your kind invitation. Yes, I'm Will Marshall, as Jada introduced. I began most of my background in physics, so I was really interested in mathematics and physics and mainly astronomy when I was younger. I've known Jada for many years, and she's an inspiration to me as well, so the compliments are returned. But yeah, I got interested in astronomy. I went into that, did my master's and PhD in physics as well as my undergraduate, and then ended up moving to work at NASA on a number of spacecraft missions, mainly lunar missions, looking for water around the moon, which we actually find water around the moon, which was exciting, and missions to test new technology in space, and it did with us, our team. I was very interested in astronomy when I was a kid, and ended up pursuing that into my career. I first got interested in astronomy when I was maybe about 7 years old. I ended up building a little telescope when I was maybe about 16 or 17, and then studying astronomy at university, and then did my PhD in quantum physics. So more like the opposite end, the smallest scale at parts of the universe. And then ended up working at NASA, where we were trying to do some cool technology missions. Firstly, we sent a little probe to the moon looking for water, and we found lots of water on the moon, which was cool. I was spending some time working on orbital space debris, which is a bit like the challenge in orbit, like our environment challenge on the Earth, where all the stuff that people have put up into space over the years is coming back to hit each other, and so we have a bit of a challenge of environmental challenge in space, and so how do we stop that? And then finally, I was working on some technology demonstrators, and what I was trying to say on the video was that we ended up sending some phones into space to see if they would work, because we realized that the cell phone that you have in your back pocket has most of the technology you need for a satellite. It has GPS, it has cameras, it has radios, it has accelerometers so that you can play the games. It has a computer, of course, and hard drive space. It has much of what a satellite needs. And so we were intrigued about whether or not they would just work in space. And since NASA was typically spending, oh, I'm going to mute that. Since NASA was typically spending maybe $1 billion per satellite, and we were just, oh my God, that's just crazy. Maybe it could be done at lower cost. And so we sent some of these mobile phones into space, and they worked just fine. And we had amateur astronomers all around the world pick up the pictures that were taken by the phones, and then we were like, oh my God, we can make this much different sort of capabilities. And that's when we had the idea of doing Planet, which I was going to try and share my screen and show you. Hopefully I can share this and show you a little bit. What we set ourselves as a goal when we left NASA was to send up enough cameras to image the whole Earth's landmass every single day. So every point on the Earth land, so that we could track and see changes across the world. And why did we want to do that? Well, we thought that if we could do that, we could do things like track deforestation and stop it, or track illegal fishing and stop it, or help people in farmers, and 25% of the land of the Earth is farmland, help them to improve their crop yield and things like that. And so we thought that there was a lot of uses if we could image the whole world every day. And so over the last, so we started Planet about 8 years ago, and we have launched over 300 satellites since then on 26 rockets. So we put our satellites on when other people are launching their big satellites, we put our little satellites around the side, and we've launched these in space. And now we, in fact, did reach our mission that we set ourselves of imaging the whole of the landmass of the Earth once a day. Now, because of clouds and things, occasionally it takes a couple of days before we can really see any particular place with a beautiful cloud-free image, but generally we try and take a picture of everywhere, every day. So that's taking a picture we're simply 500 kilometers away, and our telescopes are about 10 centimeters by 10 centimeters by about 30 centimeters. So they're little box satellites. We can just about see a tree. And just about see a car. So you can't see a person, or you can't read a number plate or a newspaper or something like this. But you can just about see a tree, and that helps us to do those things like tracking deforestation or tracking ships and things like that. So the most important thing I have found in this journey is the motivation. And so what motivates us in our team at Planet is all about helping the world. And so we sort of consider our mission using space to help humanity, whether that's those things like protecting parks and stopping deforestation or illegal fishing, through to helping people improve their crop yields, through to tracking refugees in refugee camps, helping people to access water, helping with peace and security, and even shedding light on situations like the global pandemic of coronavirus. And I'm just going to show you a few pictures related to that as well, if I can get this technology working. But maybe before I do people have any quick questions while I'm still trying to reboot this technology?
Yeah, how do you point the telescopes? Because if you have a telescope with relatively high magnification, you have to keep it pretty stable, and I'm wondering how you do that.
Mm-hmm. Yeah, very good question. Basically, we have little reaction wheels. The reaction wheels are little wheels that you turn them one way and the satellite turns the other way to conserve momentum, because you're in space, there's no friction, and so they turn it around. We actually have another system which is even more cunning in a way, which is we could make these little coils of copper wire, and if we put a current through them, it would cause a little magnetic field. And that little magnetic field reacts against the Earth's magnetic field and turns the satellite slowly around. So we have those two systems. So if one doesn't work, we can use the other system. So little reaction wheels, as we call them, and magnetometer coils.
Okay, so my question is basically, since they're so small, these satellites, I imagine they don't have rocket boosters to keep them in orbit. And if they don't, how long can they stay in orbit for?
They stay in orbit about 3 or 5 years, and some of our satellites, about 20 of them, do have propulsion on them as well. But most of them, you're right, don't. And yeah, they last about 3 or 5 years, and that's just dependent on the altitude that we put them in to start with. Set ourselves this goal of imaging the whole Earth every day. This is how the system works. So put all the satellites in one plane, a polar orbit, so it goes over the pole. And each one takes a strip of images, as you see across Africa there. Each one's taking a strip of images as it goes around. But by the time the next satellite gets there, it's just the Earth is rotated underneath. And so it ends up being like a line scanner for the planet. The whole system acting together takes a picture of every point on the landmass once per day. This is a rocket launch, which can give you a sense of how it works. This is an Indian rocket, a PSLV. It took off. It was all sped up. It takes about 10 minutes to get to space normally. That's sped up into 10 seconds. But here's all the little satellites coming out of the back as we eject them, and then they turn themselves around and start looking down and taking the pictures downwards. We have, this slide is just to show that we have a lot of data. We take over 1 million images per day of all the Earth. It's actually now over 10 terabytes every single day, and over 27 rocket launches. We got to our mission one success about 2 and a bit years ago. And so now, for any one location on the Earth, as you can see in this picture of Los Angeles, we have hundreds and hundreds of pictures. And actually now we've got over 1,000 pictures for every location on the Earth's surface, so we can see changes. I'll just play that again so you get a sense. This is just all the, of course, ships going into and out of the port of Los Angeles. The uses of this data, I've talked about agriculture a little bit. Maps is, we help companies like Google to improve the maps. So if you look on those maps, often they'll be updated using our data. So when they find a map is out of date, the house is old, or the road has changed, they use our satellites to find a new building or the new road and then update their maps. The governments use it for various things. So, for example, we work with coast guards on monitoring fishing or border security, or we work with governments to understand disaster response. There's many other places that we work. I just wanted to show a few pictures just so you get a sense of what it looks like. And then the pictures I'm going to show here are pictures all related to the coronavirus and what's going on around the world as seen from space. Of course, it started in Wuhan. And this is what Wuhan train station looked like in January. So it's quite, you can see that all the trains and all the cars along the road. But if I go to late January, just a couple of weeks later, you can see all the cars have disappeared from the roads. So basically, everyone's just left the streets. So that's before with all the cars, and then afterwards with no cars. Here's the bridge, which normally is full of cars and no one in it. Here's Mecca in Saudi Arabia. It's a place where everyone goes. Muslims go to there, and if you see all the people around right in the middle of Mecca, that's in a normal day. And here is just a few weeks later. So this is the end of January, and this is in March. So you can see the people just disappeared from the middle of Mecca there. This is in Cairo, in Egypt. Again, you can see all the cars and the activity, and then a few weeks later, everyone's gone. Central Park in New York, they were erecting a hospital. So this is look before, and then this is afterwards. They erected that hospital. Here's an airport. Of course, most airplanes spend most of their time in the air. They don't spend much time on the tarmac, and this will show that they stacked up. In a second. Anyway, those are a few examples of our imagery. Our data isn't central to helping with the coronavirus. We can't obviously see the virus from space, but the most important use cases of our imagery, honestly, are all to do with the humanitarian ones. And the world has put together, all the countries of the world came together and established what's called the Sustainable Development Goals. I don't know if you've studied that in school, but they're the biggest and most important goals, like ending hunger and helping protect the environment and things like that. And we've assessed that of those 17 big goals, we can help with 13 of those goals. And so that's the thing that keeps us most motivated is, so we work with the UN, we work with NGOs to help them to as best we can meet those goals as quickly as we can. Great. This is the one I was just showing you. If you see, this is before, so this is in December and this is in March. You see all the extra planes that turned up. In some cases, we saw them stacked on the runways because the airports didn't have enough space. This is a normal day at Disneyland. This is the car parking lot of Disneyland. You can see the Disneyland at the bottom. And this is in March at Disneyland. And this is what I was mentioning about the Sustainable Development Goals. We can help a lot of those goals. I'll give you a few examples. This is deforestation in the Amazon that we can capture. And this is refugee camps being built. Of course, that can help to help. A lot of poverty is to do with people in refugee camps and refugee flows, and so helping NGOs like Amnesty International understand those can help them to bring relief to those camps. This is, of course, a lot of important things for people is access to clean water. This is a reservoir. This is just 2 days, 1 month apart. You can see the reservoir before in February and then in March go down. The levels of expert. This is studying glaciers, which is of course related to climate change, and we can help people track that. That's the same glacier a couple of months apart. This is deforestation, tracking deforestation in time. It's not just that we can count every tree, we can actually estimate the amount of carbon loss from the atmosphere. And then recently, we did some work classifying all the world's coral reefs. So we did a first high resolution image and a dissection of all the different types of coral reefs around the whole globe, and then gave that to scientists. And then they can monitor it more regularly to check if there's any illegal fishing or any signs of ocean bleaching, which can hurt the corals and therefore the wildlife around them. Tracking illegal fishing. I just wanted to say at the end just what we're working on next. We had set our first mission to image the whole Earth every day. The next thing we're doing at Planet is figuring out how we can index everything on that, in that data. So you know, Google index what's on the internet so that you can search and find out whatever page you need, any information you need. What we're trying to do is somewhat similar for the whole Earth, all the physical things on the planet, so that you can ask questions of what's on the planet. Let me just say a little bit of how this works. So a bit like Google can help you find cats and dogs in images. We're doing the same with our satellite data, and this is we can recognize trees and ships and planes and trains. And then if we do that every day, we can build up a database of where everything is on the planet. And then you should be able to just ask questions about that data, like how many planes are there in all the world's airports, or how many ships are in all the world's ports, or give me a plot of that versus time. And it should be able to help you to understand all those things. So that's really where I wanted to end this presentation today, and then turn it over to questions. Sorry again for all the technical difficulties.
Thank you so much. That was really good. Okay, we'll just go with Connor.
Yeah, phenomenal presentation and really great work. It's quite amazing to see. And if I remember correctly, I think either you said or the TED Talk that was open source. And so, but my question to you is just from what are the concerns that have been met from a privacy standpoint? Like in terms of how could this be used to actually like monitor people like on a deeper level? And like I said, I think the work you're doing is really amazing, but I'm just curious to see what are the comments you've had about privacy with your product, and how have you resolved those?
It's a great question. I'm glad you asked it, Connor. So basically, the resolution, I was mentioning this, I'm not sure if I had gone offline or not at that point, but our satellites are 500 kilometers away. So it's about the same distance from San Francisco to Los Angeles. And our telescopes are about this big. So you really can't see a person at that distance with that telescope. And in fact, even if you launch the biggest satellite that you can fit in the biggest rocket, you wouldn't be able to identify a person from space. It's just not high enough resolution. With a drone, where you're really quite close down, you can do that. But in the case of a satellite, you're just too far away to identify a person. Now, that doesn't mean there's no privacy implications, because for example, you might be able to identify vehicles. And if you know that a person is associated with a vehicle, maybe you can track them. But generally, it takes much more than just the satellite data to do that. And so we're concerned about that, but it's generally not a big concern because of the nature of our resolution.
It's more about trends, not individual people, correct?
Yeah, so exactly. We could see big sets of people in marches, or we could potentially track vehicles over time, which if you had other data to associate a person or people with those vehicles, it might be possible. But generally, it's not the way you might think, and that's because you can't see the person at all in the image.
Yeah, thank you.
Sophia?
Any other questions?
Yeah, Yeah, so you were talking about launching like your own self, how you could launch like a cell phone up into space. If you wanted to kind of do your own project to create like a satellite back home, could you launch like hypothetically launch some sort of device from your like by yourself, or do you kind of need a giant rocket in order to be able to get things up into space?
Yeah, I've been working on my right arm to make it stronger and stronger to float into space, but still haven't made it work. No, in general, you really need a big rocket. Yes, absolutely. There's no way you can get into space without a rocket. It's very difficult. Roughly speaking, the satellite on the ground has to go from 0 meters per second on the ground to 8 kilometers per second to be in orbit around the Earth. And so that is a huge velocity, 36,000 miles per hour, to put it into miles per hour if you use those units. And so to get to that speed, you need a rocket. And so, yeah, we have to use rockets to get to space. So it's not something you can easily do. But increasingly, people are making more standardized packages, and the cost of launch is going down. Typically, it used to cost about $20,000 per kilogram of the mass of your spacecraft going up into space, and now it's come down to about $5,000 per kilogram. So it's going down. It's not cheap, but it's going down.
Okay, that makes sense. It just popped into my head. This is also a great presentation, so thank you.
No problem.
Looks like Matthew has a question.
Thank you. First of all, sorry about the background noise. Am I allowed to ask more than one question, or do I have to like put my hand down and then come back up again? Jada?
I say just go for it. Don't ask like 10, but within the
okay.
Yeah.
So first, you mentioned that they have a relatively short, use period. Is there a plan for decommissioning them, or are you just going to let them like burn up in space? Or
yeah, so we deliberately re-enter them into the top of the Earth's atmosphere, and they burn up. And it is a little bit of pollution in the sense that the satellite just turns into gas in the upper atmosphere of the Earth, but it's very, very little. And so that's better than staying up in orbit and being a long-term space debris hazard. Does that make sense, Matthew?
Yes. Also, do you have plans for like further decentralization of satellite networks? I know currently, the majority of GPS satellites are government run. Do you have plans for, smaller decentralized GPS satellites or any sort of expansion?
We have no immediate plans for GPS satellites, but it is true that somebody could do that. I mean, I think generally those systems are very well run by the government. I'm not sure what you would do that's added value compared with the commercial government ones, but since they are freely provided by the government, there's not much of an incentive for a commercial client to go into it. There's some limits of GPS, like for example around tall buildings, it doesn't work very well because the signal bounces off the buildings and then the GPS gets confused. So in certain cities it gets confused. So there might be some applications, or maybe there's some applications where you want higher resolution. But generally, I would say it's not a big commercial area.
Okay, and then just kind of one final question. Connor mentioned the privacy concerns earlier. Do you have a way to, block off people's land, like so that you can't I own like, a 200-acre plot of land somewhere. Can I contact you and say, I don't want images of this land on your server?
Yes, you can contact us, but no, we will not do that for you. Because it's not just you that is interested in that plot of land. There's many people that are interested in that plot of land. Everyone is concerned. Ultimately, the Earth has to be taken care of, and your plot of land is important for environmental concerns. Of course, governments are interested in it. Whether it's an agricultural piece of land, maybe they're interested in understanding how food production is going or what have you. And so no one can block anyone else at the present time.
Okay, thank you.
All right, Alana.
My first question, I guess a little bit similar to the privacy concerns, but I guess if it's open source, do you have kind of like a way to make sure your data is not used for malicious purposes, oppression or segregation? Do you have any sort of like safeguard place?
Can you help me understand what do you mean by oppression? What sort of things might you envision it being used for?
I guess I'm kind of envisioning like using the satellite data to kind of image like certain parts of an urban area, or in like maybe like a less developed country, and kind of pinpointing areas where maybe like people are living, and then on the ground using that to your advantage, like making sure people aren't, I guess I don't entirely know, but I feel like you could kind of like try to like corner people so that, and then use satellite imaging to make sure that they kind of stay in an area where they can't get out of and are forced to do like lower wage labor or like unpaid labor because you like get rid of resources around them. Yeah.
Well, it's a very interesting question. I've never heard quite that question, so thank you. But broadly, let me say a few things about technology and society a bit more broadly to frame this, which is that, you know, many people say, well, technology can be used for good and bad. Every technology, a knife can be used to help you eat, or it can be used to stab someone. But I think very strongly that that's only half the story. Actually, the most important thing is that each technology is bent towards more positive applications or more negative applications, depending on which technology it is. So, for example, nuclear technology has benefits and problems. Benefits like medical imaging, that if you go into a hospital, you can get imaging that's based on nuclear technology. But costs and challenges like nuclear weapons, which could destroy everyone on the planet. And in my mind, the negative implications of that technology far outweigh the positive implications. So if we could snap our fingers and the whole technology disappear, that would probably be a net positive thing for humanity. I would prefer to not have those medical benefits in exchange for not having the existential risk of nuclear warfare. If I can extrapolate from that, satellite data is very much bent towards positive applications because of the resolution and because of the ability to scan large areas. Now, just like every technology, there's potentially bad use cases. I mean, I think the one you're hinting at there is one where it's about, you know, information asymmetry of a government or something like that that could help push and repress people. And the most important principle we take on our data that might help stop that is that we will never sell our data to one person and say nobody else can have access. We never do exclusivity. So if a government says, hey, I want this data of these people, and you mustn't give that data to anyone else, we will say no. We will say, no, we will sell it to you if you want it, but we will also sell it to the other people. And that's important because that means that in principle, other people can get access to their data. And therefore, it doesn't lead to the asymmetry, the information asymmetry that might help governments repress people, for example. Now, I'm not sure if that's a full answer because I'm not sure enough about what you had in mind, but that's sort of my general response, if that helps.
Yeah, I really loved hearing your thoughts on like the kind of impacts of technology. Yeah, thank you.
Ben?
Hi, thank you for sharing everything. It's been really interesting to listen. One thing I want to talk about was that I know you mentioned I believe you did some research in space debris at one point. I was wondering if you could use your technology to like track space debris and help cleaning efforts. I was wondering what your thoughts were about that.
Yeah, it's a very good question. Actually, it's not ridiculous at all. There have been satellites launched just for looking at other objects in space debris to track them. and actually very similar sort of satellites to our own. So instead of looking down, we could turn them out and look at other space objects. Now, that's not their main mission. We really focused on the Earth. We want to help that most. But similar technology could be used. So we're focusing on the customers that we have on the ground, but similar technology could be used for doing tracking of space debris. And that could help the problem, because the more accurate you know where all the objects are, the more likely you can predict collisions accurately, and then make maneuvers of your spacecraft to stop the collisions. Now, the trickiness with space debris is actually that most of the objects aren't satellites. So roughly speaking, we have about 2,000 active satellites in orbit around the Earth, okay? And planet ourselves, we have well over 100 of those satellites ourselves. But there's about 100 million pieces of space debris, all the stuff from previous satellites, flecks of paint, or a satellite where you left with fuel in it and then it accidentally explodes later on, and then explodes into lots of little pieces. And the problem is, unlike on the ground, if a plane explodes, all the stuff falls to the ground, or if a ship breaks up, all the stuff falls to the bottom of the sea, or if a car crashes into another car, it just falls on the road. In space, if two satellites collide or two objects collide, they splinter into thousands of pieces, and then they just carry on orbiting in the same orbit, very roughly. And that means that those things stay. It's like if two cars collided on the road, and then all the stuff that they made just carry on the road, going at 70 miles an hour along the road for the rest of their time, and be just a pest for everyone else. And so it is a challenge. And the more accurately we know where that is, the more accurately we can stop future collisions.
Okay, that's really interesting. Thank you.
Rami.
Okay, so I was interested in if you had thought of whether launching these satellites with weather balloons. The reason I thought of this was because I recently, like, the world record for the highest skydive was broken with a weather balloon, and that had to take a capsule carrying a man, and that weighs much more than 4 kilograms, which is the weight of the satellite. So could your satellites be launched with weather balloons?
It's a great question. So actually, there are some companies that are trying exactly the idea you just had. So they would launch up with a balloon and carry a rocket underneath that would carry the satellite into space. Now, the balloons actually don't go very high compared with space. They go, those balloons maybe go to 30 or 40 kilometers up, but space really starts, well, legally it starts at 100 kilometers, but most satellites can really only operate after a few hundred kilometers. Our satellites are mainly between 400 or 500 kilometers, so about 10 times higher than the balloon goes, is the minimum altitude that you can operate in space. And so they're not high enough. And the most important thing is that in orbit, your velocity is tangential to the Earth. It's parallel to the Earth's surface, if you like, as opposed to the balloon goes up, right? So it gets you up a little bit, but it doesn't get you the sideways velocity. And to get to the sideways velocity is the hardest part, actually. That is the 8 kilometers a second. So actually rockets, when they take off, they go slowly, slowly, slowly through the atmosphere, and then they accelerate really fast to the side. They bank over and accelerate to the side because most of the velocity is sideways, but they have to get above the atmosphere. So the balloon helps you get up above the atmosphere, which makes it easier to go fast, but you can't, it's not enough to just go up. So it helps a bit, but not very much.
I understand. So it wouldn't be practical. You'd anyways need a rocket. Thank you.
You still need a rocket.
It's fantastic.
Hey, thank you.
Reed.
Hi. I wanted to thank you for coming. I think you're doing some incredible work. So I'm wondering, with all of this data that you have collected, what kind of like interesting or surprising things have you been able to do or put together, or things that clients are using your data for?
Oh man, there's so many things. Some of the things that is being used for, we could foresee. like tracking deforestation, but other things we couldn't foresee at all. One recent example was we're working with some foundations who want to use our data to track tropical diseases, mainly in Africa. And we were like, well, how on earth can we help track a disease from space? You know, obviously we can't see the disease itself. But it turns out that the tropical diseases are strongly correlated, in this case, with stagnant water in rivers and on banks of rivers. And the most important correlation with outbreaks of disease is stagnant rivers and proximity to nearby villages. And both those things we can see in our satellite data. And so with a grant, we managed to get them access to a lot of our data. We gave a whole bunch for free, in fact. And then they have been using it to track tropical diseases. And I would never have ever expected that, because obviously, as I said, you can't see the disease itself from space. But we are trying to help where we can with things like that.
Yeah, that's really interesting. And I have another question, and it's on the security thing again. And I definitely agree about the trade-offs with technology. But I'm curious, I looked on your website and I saw some of the stuff that you do has to do with insurance and questioning risk, financial things, collateral. And I'm wondering how that works in terms of the actual person who is, I guess, being monitored, or the different things being, I guess, insured and that sort of thing, of whether those types of people know that they're being monitored, and how that works, I guess, with watched.
Yeah, it's a great question. Yeah, it's a great question. Generally, what we're doing in areas of insurance is things like claims monitoring. So in agriculture, if there's a big flood, the farmers have insurance that in the case of a flood, the insurance will give them money so that instead of the earnings from their crops that they would sell on the market, they can get some money to feed their family or whatever, you know. But sometimes there's fraud in that, and they will claim that a flood has hurt their field, but it hasn't. And so the insurance company will use our data to look at the field to see if there's a flood or not. And that's cheaper than sending a person, which is what they used to do. So they used to send a person out to the field to see if there's a flood or not, to check if the farmer's claim is correct. And now so how does that, you know, impinge upon privacy and security? It's interesting. I mean, generally, the farmer in this case has opted for the insurance, so that, and they probably accepted at some level that they need to be checked if they ask for money for that off that insurance policy. Does that help at all?
Yeah, and I guess it's also going to work out for the farmer in some way, because they would have probably lower rate.
Yeah, I mean, don't get me wrong, big companies can always potentially try to hurt the little guys, and so maybe in some cases it could, but I can't think of, at least in the way I've understood it to be used, I can't think of an obvious case.
Yeah, that's interesting. Thank you.
Victor.
So I wanted to ask about the satellites. You said that most of them stay in space for about 3 to 5 years. So I was curious, how do you protect them from radiation?
Great question. Actually, mainly we don't. So the quick answer is that at this altitude, the Earth does the protection itself. So there's these things called Van Allen belts, discovered by a scientist called Van Allen, which exist higher up in what's called medium Earth orbit. And around if your satellites are under these Van Allen belts, actually most of the tricky radiation that can be disruptive for electronics is stopped by these belts. They're belts of charged particles that basically the other charged particles can't go through, or less easily go through. So in a way, the Earth has put the shield up, and we're operating below that shield. And then the second thing is that just with our little satellites, we just take the attitude of putting up more satellites than we need. And if one does have a failure because of a radiation problem or a similar problem, or the reaction wheels that I was telling you about, if they fail, then we've got spare satellites. It's obviously hard to go up and fix. You can't just pop up there to space and say, oh, I'll add a new reaction wheel or replace this part. But we can have a few more satellites than we need, and if one fails, it's not too much of a difference to the overall system. Does that make sense?
Yeah, that makes sense. Putting up more satellites should solve it. Yeah.
Gurmahar?
Yeah, my question was regarding what the next step in all of this might be. I mean, from what I understand, that there's this one sort of circle of satellites that orbit relatively perpendicular to the ecliptic. So would another step be to say, if you added another of those circles to get more rapidly updating images, perhaps twice a day, and in the future, I guess some sort of utopian thing would be real-time imaging, even though it's a long ways away. But how do you have any plans to advance this more than one time a day?
Yeah, absolutely. So it's a great question, and the answer is yes. Very much our goal. There's actually 3 ways you can improve the satellites. One is spatial resolution, one is temporal resolution, and one is spectral resolution. So the spatial resolution is the size of the pixels on the ground. Is it 1 meter, 10 meters? The temporal resolution is how often do you visit, once a day, once an hour, once a week. And the spectral resolution is how many colors can you see? Is it just black and white, or is it black and white and color, or is it other spectral bands that are beyond the human eye can see? And in fact, we are trying to get better and better in all 3 of those axes. So, for example, most of our satellites have 4 color bands. They can see 4 different colors. 3, the same as the human eye, red, green, and blue, and 1 called near infrared, which is just off the optical spectrum, which helps us to tell things about crop. Basically, we can tell how much biomass, we can tell crop type, crop yield, and how much biomass, how well crops are doing from space with this particular color. But we're also trying to improve in temporal resolution, which is what your question is about. So we would like to get to every hour instead of just every day. And in fact, we have 2 rockets going up in the next 2 months that enable us to get much more rapid revisit of the Earth's surface towards that goal. And then on spatial resolution, we're also trying to improve the resolution of the images. So the best resolution images we have right now are 70 centimeters across, and we're right now upgrading them to be 50 centimeters across, so we can see something 50 centimeters is the size of a pixel on the ground. So yeah, we're trying to improve in temporal resolution, and yes, if you added another plane, you can get to twice a day, or if you add 10 planes, you can get to 10 times per day.
Yeah, that's wonderful. Wow, one time an hour would sort of be, I guess, that'd be amazing. I mean, constant updates. And then, given that you mentioned spectral resolution, I guess, would it be possible to add, I guess, receptors for UV light, and then that could help monitor the ozone layer, or are the satellites not far up enough to do any sort of monitoring on that level?
Actually, yeah. So right now, generally, our satellites cannot see different types of gases. So they can't say this is CO2, or this is ozone, or this is methane, or other. We would like to be able to do that, but right now we can't. And so that's what. And for that, we need this, what I was calling about spectral resolution. The more different colors we can see, actually, it enables us to tell the different gas types. And so we're working on that as well. We have a project with the foundation to try and see if we can see lots of different colors, like maybe 100 different colors. And then with that, we would be able to see if there's certain gases like that.
Awesome. Thank you so much.
And we don't want to keep it for too long, so let's have Matthew.
Okay. Sorry, I'm a little bit of like a legal nut and kind of curious about the international law implications of this. Yeah. So one, I know particularly like some places like France have fairly strict laws regarding, sorry, I'm blanking on the word, like copyright laws regarding buildings, and particularly when buildings have like innovative designs. Given that I presume you're selling the data you're collecting, how do you get around these kind of laws, or how do you make sure you're not in violation of those laws?
Well, interestingly, space is quite an interesting case for law, and I encourage you to take a look at it. There's actually some really interesting space law courses, one at the University of Montreal and one at University of Leiden in the Netherlands, can tell you all about this. But basically, there's not very much space law yet. But one of the things it says is that if you put a satellite in space, you can take a picture of anyone's country without their permission. And so in effect, you are in international territory. You're not really in a country, so you're not subject to the country's laws. It's like if you, instead of being in France and violating that law that you're referring to, you're actually in England and you're taking a picture from England of France, and therefore where you are, you're not subject to the law. So in space, you're not in, even if you're above France and you can see France, you're not in France. You're actually in international territory. This is also similar to the high seas. So if you're over 12 or nautical miles from the shore of a country, you're actually in the sea, in the high seas, and then you're not subject to national laws. There's actually an exclusive economic zone that goes out 200 kilometers, but in the middle of the ocean, you're not subject to a national government. So this is sort of a very different territory. And one of the things early on that the Russians and the US agreed was that anyone can take a picture of each other's country from space. They couldn't do it from the plane. Like if you go over in a plane, you have to get permission from the country you're flying over. But in space, you don't have to have permission. But one of the reasons is that you can't come up to Russia and just turn left in your satellite. The satellite is going to go over Russia, and you can't really know whether the satellite's taken a picture or not. And so and the other thing is that they're just a long way away. And for these two reasons, Russia and the US agreed, okay, well, we'll let each other's satellites fly over each other's territory. And then that became international law, that anyone can fly over any territory. So we can fly over North Korea and take a picture of North Korea, and the North Korea government can't say, no, you can't. Actually, they have no choice. And nor does, and so sort of similar way, the copyright law or law you were mentioning can't affect this situation.
Okay, thank you. Just sort of one other question. So you mentioned you're working on like 50 centimeter pixels. Will that allow you to see like objects as small as 50 centimeters across, or?
Yeah, just about. So, okay. But you have to be like what a pixel is. So that's one. You get one piece of information for that. And normally, so for example, to identify a person from their face, you would at least need many pixels per of their face. So you would need maybe at the minimum sort of 1 centimeter resolution. So about 50 times better than that. And that's why we still couldn't identify a person from space, even if we could, if they spread out on the ground, maybe we could just about in principle detect that they were there. You couldn't say who it was. Does that make any sense?
Yeah, thank you so much. Great talk.
Okay, maybe your last question, Sophia.
Hi, yeah, so I just had another quick question. In terms of any astronomy from the ground, do the satellites, sorry about the background noise, my sister's running around, but
okay.
Does the, now I'm blanking, but do the satellites actually impact, like the reflection of the satellites impact any ground-based astronomy, like the reflection of the bottom of the satellites impact any of that?
It's a great question. So generally, the chances of it affecting astronomy are very low, because the chances of the satellite being in the view of the telescope on the ground at the time when they're taking a picture is very, very small. But there has been problems recently. In particular, astronomers have been upset about the Starlink satellites that SpaceX is launching. And this is for this reason that you're mentioning. They pass in front of the telescope, and then there's a big streak of light. Actually, satellites are very easy to see in the sky. If you look up at night, especially just after sun has gone down or just before sun comes up, if you just look up, and especially if you look north towards the pole star, if you're in the northern hemisphere, anything that looks like a plane, except it's just constant and there's no blinking, that's a satellite going over the top. And if that goes across over the the telescope on the ground where it's looking, that'll just look like a load of light, brighter than the objects that they may be looking at. But for our satellites, because they're so small, they don't really cause astronomers very much problems. The challenge with the SpaceX satellites is that they're very, very big. They're 10 meters across rather than 10 centimeters across. And so that makes a big difference to the brightness.
Okay, and if you need to go, I think Martin had one quick burning question, but after that, then
okay, let's do that.
All up.
Okay, that sounds good, Jada.
Okay, I just wanted to ask about the RGB channels. Okay, so I know some satellites like the GO-16, they have a small delay between the capture between the RGB channels, and so that kind of messes with the alignment of the image. Do you guys experience any sort of issues like that?
Actually, yes, on some of our satellites we do. We have 20 satellites we have a similar system to that. And so when we see objects moving, when we take a picture of objects moving, it is true that we capture the red, the green, and the blue at slightly different times. And therefore, if something's moving fast, we get 3 different images of it, and then they all overlap. And it particularly happens with planes. And you can see the plane will look like 3 different planes of 3 different colors in the picture. And in fact, if you zoom around on Google Maps, if you put the satellite layer, you can actually find some of these anomalies. If you just search on Google for planes in flight on satellite on Google Maps, you will quickly turn up a bunch of these anomalies. So yes. Well, let me just say thanks to you guys all for all your time. Thanks for listening. Sorry for all the technical challenges at the beginning, and I hope it was interesting. And I do encourage you all to pursue your interest in science and mathematics, and I have not regretted in the least going into that area. I think one of the things that's so fantastic about mathematics and physics is that they're very applicable to a lot of different areas, so it keeps your options open. Obviously, I'm biased, but it's been great training for me. Even though now I'm mainly doing business, I still find it useful, and I still have my calculator by my desk to check mathematical calculations here and there. And so it always comes in handy every day. And I would also say that if you're interested in learning more about space, I can send some more links and things. Like if you're interested in space law, you know, as I mentioned, Leiden and Montreal. If you're interested in technology and society, we have many questions about privacy and things like that. I'm so glad that you guys are all interested in that. We need more thinking about how technology interfaces with society. Very broadly speaking, humanity has invented all these amazing technologies and gadgets, but we don't really have good systems of how to govern them, of the law and of all the social norms to adopt them. And so I think it's really encouraging that you guys are all excited about that. There's lots of great courses, including at Stanford, by the way, on technology and society, or the history of technology, or technology ethics. Those are the sort of key terms to look for. Technology and society, technology and ethics, and the history of technology and society. If you can look up things like that, and of course just general ethics courses in philosophy, you'll, I think, learn a lot, and it'll be very, very useful, as well as the mathematical side of things. So I think that understanding the social implications of technology and societies is as important as understanding the technology itself.
Thank you so much for an amazing talk, Will. It was really nice having you kick off the mentor talks.
Hey, no worries at all. Pleasure to meet you guys all. Good luck in your career.
All right, bye everyone. Thank you.
Thank you.
Bye-bye.